obvious way the set of its critical values. It is exactly the set of points of projective on projective line where the cardinality of pre-image is oh, sorry, please excuse me, the strict inequality should be written here.
А можно попросить права на запись?
Sorry?
Я прошу права на запись зума.
Я сделал вас ко-хостом.
Спасибо.
Нет, я не возражаю. Yes.
Recording in progress.
Yes, got it. Okay. So, suppose that the definition of the set of critical values is correct, not like it is written here. Now, as for the different views, in Arnold's school that perhaps is dominating here, the tradition is to consider the functions that have a rather large set of critical values. What is drawn here is the extremely large, as large as possible, but it is traditional to consider, well, the non-standard ramification over 1 point or over sometimes over 2. As for the other extremity in the theory of descent d'enfant, which we today's speakers represent, we consider the opposite. Usually we consider the opposite case where the number of critical values is as small as possible. It means that it is 3, and moreover we normalize it. Sorry, I'm afraid that it is not seen. Yes, we normalize it in such a way, traditional way, that the critical values are 0, 1, and infinity. Now note the technical assumption we'll use during all the talk is the concept of the clean Belyi pairs. It means that the ramification over the branching over 1 is always twofold. It follows, of course, that the degrees we consider are always even. And what I was trying to write here, to draw here, is that otherwise the branching is totally arbitrary. And well, I'm writing the passports in a bit non-traditional way, in such a way that the columns reproduce this geometrical picture as the multiplicities over the branch points. So these are two extremities, and basically the talk is about what is written here, what lies between. Yes?
I was always puzzled. Why do you call this clean Belyi pairs? I would choose pure.
Oh, I have discussed it with English-speaking people, and was told that that both words are good for this situation. However, clean is rather means physically clean, while pure means mentally clean or something like that. So, well, I was considering this question, and I found that the English-speaking authors usually use the word clean. Well, in Russian we have only one kind of cleanness or pureness. So we are going to discuss what lies between these extremities, however, sticking mostly to our extreme. So now some generalities about these objects. So for, well, we work with three integer parameters. D and G were already introduced. As for B, it is the the cardinality of the branch set, the set of critical values. So we consider the filtrations of moduli space. Sorry, here G is the most fixed of the three parameters. So inside the moduli space of genus J, we fix D and then consider various B's, well, from one extremity to the other. This extremity is, well, according to the well-known theorems of algebraic geometry, every curve has a rational function and a Morse rational function with this number of critical values. So now, briefly, the general problems that can be related to this construction. So I grouped them into four classes according to the various branches of mathematics. As for the combinatorics, we know that a great activity was devoted during the recent decades to the cardinalities of sets of Belyi functions, Belyi pairs of given genus and given degrees. Though usually these problems of these cardinalities is formulated in an equivalent way in terms of graph on surfaces. In fact, I think we will use the Grothendieck equivalence between Belyi pairs and graphs in surfaces only technically. Our main heroes are Belyi pairs. Now, as for algebraic geometry, all this bunch of sets carry the structure of quasi-projective manifolds. And there are lots of questions about them. We'll specify some. Now, as for arithmetic, it is maybe not so clear in this audience. So I briefly say that all the strata are defined over the fields of algebraic numbers, and there is a question exactly over which. They are acted upon by the absolute Galois group, and the most popular problem in the theory of descent d'Enfant was the study of this action on the Belyi pairs itself. Well, and the other, I have said recently that it is profitable to consider the objects over various fields. So there is a delicate problem of primes of bad reduction. We consider these, in fact, algebra geometric world constants, and we are interested in what happens with them when we reduce them moduli various primes. And finally, the obvious topological questions are natural in any mathematics that happens inside the moduli space of curves. And well, the most popular problems of the recent decades, marked by several fields prizes, concerns the homology and their intersections. And well, the hosts of these seminars contributed a lot to this problem. So as for foundations, I mean the foundations about concerning the critical filtrations. Okay, now, as I said, we'll keep close to the dimension 0 and mainly concentrate on the dimension 1. So the next case is the case of pairs with 4 critical values. Then the components of the corresponding subsets of moduli spaces are curves, and they constitute the freed nets. That's what I tried to draw symbolically. Here, red points are Belyi pairs, and they are connected with the components of the freed net. I would say that this structure is studied to a very small extent. And in fact, the main goal of this talk that is represented in its title is напомнить завтра. Well, and the main result is just one calculated example. Now, a couple of special problems that definitely make sense in the case of curves. First of all, the components have their genus, and the birational classes of curves are totally, well, the discrete invariants are totally defined by their genera, and any curve, the punctures of the curves mean just the intersection with the boundary of moduli spaces. Also, the object very well studied in general during rather many decades, but with rather small concrete results about the objects we are discussing now. So, now what is special with the case of genus 2? In fact, it's just the smallest value of genus when this picture makes sense at all, because in the, well, in smaller genera, just nothing like this can be drawn. The genus 1 is very interesting, but the moduli space is one-dimensional. There are no space for the structures like we are discussing. So we fix genus 2 for our further considerations for the arbitrary Belyi pairs. There is the boundary D being 5. By historical reasons, we concentrate on the case of clean Belyi functions. That means that we consider the degree 8. So there are exactly 4 clean Belyi pairs with these parameters, degree 8, genus 2. And we, again, the goal of this talk is to present the components of a freed net that cover all of them.
What do you mean by
Cover,
cover?
that means said theoretically that they are the Belyi the points in the moduli spaces correspond to such curves on which there exist pure clean Belyi functions of degree 8. And the freed nets are defined in the same way with replacing 3 by 4.
May I ask a question? So why degree 6 doesn't exist?
Sorry, why what?
Degree 6.
why degree 6
Why degree
is
6
not working?
does not exist. The functions, the freed functions of degree 6 exist on genus 2 curves, but it follows from Riemann-Gurwitz formula that the smallest value is 8. The smallest value of Belyi function is 8. So it's just a problem of non-existence.
Thank you.
Okay. Yes. The letter M in this talk is used only to denote moduli spaces, and the additional indexes always mean the subsets of it.
Значит, пространство модулей то самое, о котором вы спрашиваете. Только это уже без отмеченных точек. Но мы, то есть количество отмеченных точек равно нулю. Мы рассматриваем такие кривые, на которых существует функция степени d, имеющая 4 критических значения. Это не означает, что мы выделяем какие-то специфические точки.
Yes. Sorry, now perhaps I understand the question, and just in order to distinguish my notations from the usual one, I use the square brackets. If I'd like to denote moduli spaces with marked points, I would just use a comma.
Размерность у нас всегда один. Значит, если вы берете функцию белого, то такая кривая, такая пара, кривая функция, она изолированная точка пространства модуля. Вы ее немножко пошевелите, у вас функция перестанет быть три критических значения, а станет больше. А вот семейство Фрида – это одномерные семейства, потому что у вас 4 критических значения, 4 точки на проективной прямой, и у вас есть один параметр, который вы можете двигать. У вас критические значения, там могут быть 0, 1, бесконечности, какое-то число лямбда, которое является параметром. Так что речь все время идет об одномерных семействах.
Нет, нет, далеко не всегда. As I said, one of the questions is the genera of the components of FreeDNet, and the curve, the main hero of today's talk, has itself genus 2.
Вовсе не очевидно, что это однопараметрическая вещь, но параметр вовсе не обязательно пробегает комплексную прямую, или там проколотую, тем более проколотую комплексную прямую, а он чаще всего принадлежит кривой какой-то гораздо более сложной кривой.
Если уж говорить, что пробегает почти c со звездочкой, а со звездочкой без единицы. Потому что как бы, нельзя заходить в три критические значения, четвертого значения.
Нет, рационально.
Okay, so this list can be clear to the people who know the relation between descent-d'enfant and Belyi pairs. Otherwise, just skip it and just believe that we discuss for Belyi pairs. As for descent-d'enfant, they are just gluings of the octahons according to the schemes you see, and marked by the Gaussian words that will serve as their names.
In each case, we obtain a genus 2 pair. Yeah?
Yes, all of them are.
So we obtain a genus 2 surface, but
it is equivalent to the fact that there is the unique vertex. After all the gluings, there is the unique vertex.
But the resulting graph, the edges of the octagon form a graph on the set. And this resulting graph is different for this gluing.
And it is complete. There are exactly 21 gluings of octagons, and exactly 4 of them are have genus, the maximal possible genus 2. So we use them as names, and the next thing to do is to distinguish them, this small set of 4 Belyi pairs, into 2 classes, easy ones and the hard ones. As for the traditional distinction is obvious just by the automorphisms, and if we return for a while there, we see immediately that here we have the cyclic group of symmetry of order 8. Here we have a cyclic group of order 2, and here, that is not so obvious, but please believe us that there are no automorphisms. But there is a bit less trivial distinction between the easy and hard cases that needs a bit of algebraic geometry. So the Belyi functions, sorry, it is the first time where the second after that picture. Beta is the traditional notation for the Belyi function, and according to, again, to the rule of correspondence, it is such a funny function that has set theoretically the only zero we denoted by O, and the only pole denoted by infinity, underline infinity. And both have multiplicities exactly 8. And it means that the difference be O minus infinity sits in the torsion subgroups of order 8 in the Picard of X. So O minus sorry?
X here is the straight pair.
The curve on which the Belyi function beta is defined, yes. We agreed from the very beginning that X will always mean the curves we are discussing currently. This difference can have not necessarily the maximum order, and we see that the easier it is, then the smaller is the order. Or in other words, for those who understand the definition of Picard, in the easiest case, we use some new wording. So in the easiest case, the Belyi function is the 4th power of some one. In the just the easy case, it is the square of some function, and in the hard cases, it is not a power of anything. And of course, it explains easily explains why. Sorry for the clash of the words. Why it is much easier to compute the Belyi functions in the easy case. So we do it very briefly. What you see now is a bit modified result from the speaker's papers of 05. So we put the answer in the form corresponding to the subject of today's talk. It means that we find the appropriate Fried family and find the parameters where 2 critical values collide in the desired form. So this is the easiest one, and you see, as it was said before, that the corresponding, phi capital is just the freed the function that is a freed one being restricted to any fiber. So just there are the fibers that turn it into the Belyi function, and a bit more complicated answer in the easy case that also has some nice and very simple interpretation that we skip now because of the lack of time. So now we turn to the really hard mathematics, and perhaps I should say a few words about the history. As you see, the results in some form were obtained long ago, published 17 years ago, and we found them in, the speakers found them in different ways, and maybe Adrianov will say something about his methods. But the answer I'm presenting here was obtained as a result of more or less a random search, random computer search with the assistance of Stepan Arevkov, without whom perhaps these results could not be obtained. So there is a very long, as you see, there is a very long answer. What you can see is just that, 1, 2, 3, 4 polynomials just depend on one parameter t, and well, there is some information about it. We see that, sorry I didn't say it before, our hard cases are Galois conjugated. It can be deduced from general considerations without calculations, and it can be understood that the field of definition is a real quadratic field, but for the time being we don't know how to find the discriminant of this field without calculating it. It needs a slight, it might seem for a while, well, by some symmetry, the essential dependence of this pair is on t square. Therefore, the field of definition is q extended by square root of 2, and it up to certain equivalence that is very long to write down explicitly. So again, you have to believe. Again, you have to believe. For the time being, the formulas by which I can motivate it are terrible. So now we turn.
What is so interesting about this polynomial of degree 6, which appears in coefficients p, q, and r, all of them? This one, yeah.
Yes, 21t to the 6, and so no, there really is some repeating polynomial of power 6, perhaps. No. Yes, that's correct. The final step was in parameterizing some rational algebraic curve. And this polynomial starting with 21t to the 6 just was one of the components. However, perhaps for the time being, we should look at it just as at the matter of history of mathematics, because in the present calculations we move in a more systematic way than there. So I skip the symmetry reasons by which we know, well, basically they are equivalent to the self-dual, to the fact that all the descents are self-dual, and therefore all the curves of genus 2 are bi-elliptic. That means that they admit the two-fold covering of elliptic curves. Or, in other words, they can be defined as they are here by the recurrent polynomial. You see that in the right-hand side there is a recurrent polynomial. Because of its recurrence, there exists a bi-elliptic involution written like this. Well, this involution is not an automorphism of the Belyi pair, as we see from the formula on the bottom. When we apply this automorphism, the psi function is replaced by its inverse. So it is a kind of quasi-symmetry of the Abeli functions here. That is quite typical for the constructions of this kind. And well, technically it means that the function psi that is going to turn to be phi on the appropriate subset of parameters is also made out of two recurrent polynomials here, a, b, c, d, e, d, c, b, a, and here f, g, h, and a, g, f. Perhaps at this point I should stress that the coefficients f and f capital and j capital are going to play the decisive role. We don't understand now why. But you'll see it soon enough. So what we do?
Sorry, Yura. Typically, it didn't show that if a function is a Belyi function, then one over it also is a Belyi function.
Yes, and it corresponds to the dual descent.
It is true.
Yes, it's true. It's,
So that it's not having a product of two Belyi functions equal to one is not a kind of
the same Belyi function. The descent is self-dual.
the descent is self-dual.
So 1 over beta is a Belyi function of a different embedding of graph.
The graph is the embedded
There's
graph is
a
isomorphic,
morphism
but
of the
the
group
embedded
that matches one to another. But it's the same graph.
okay. So now basically the rest of my talk is a pure polynomial algebra, but with some effect that I want to emphasize. So the first steps are a bit non-standard. I've used them for the first time. Sorry for missing bracket here in the letter 4b. So usually we fix the curve and then study the functions on it. In these calculations, we reverse the process and express the coefficients of the curves. May I remind that they are small letters. and we express them in terms of the capital letters that are the coefficients of the functions. Now, after several easy steps on eliminating extra unknowns, we come to some terrible system of equations, and one of them I'm not at all sure that you can see all the coefficients of it, but it is quadratic in A. So the natural thing to do is to try to perform the base change. Here, I'll say it in two languages. In the standard algebra geometric language says that we perform the quadratic base change in such a way that this discriminant becomes a square, and in other words, the equation can be rationally solved in a capital. And well, the popular explanation is basically the same.
Will you repeat, and do not have a square, yeah?
It is not a square, yes, but it is nice. Well, it is a bit close to the square, as we see. So the decisive step is the next one. Here is, sorry, they are on the different slides, but we make this boxed expression square-free, and it becomes quite compact. So, in fact, the main open problem for us for the time being in all these, these computations are to understand the nature of this substitution, the introduction of this square root. So after that, well, some formulas become, as you see, short enough. So two more unknowns are easily eliminated. And then we approach the main hero of our talk. That is, I didn't specify where our set of parameters lived. In fact, considering some multiplicative transformations of them, we could see that they naturally live in the weighted projective spaces. Now we introduce the affine coordinates. This f small and g small are the main heroes, and now we consider the affine plane with the coordinates f, j small, and over it we have the equation like this. Now an important maybe geometric comment. Look at the delta. Our main puzzle is this delta. I have rewritten the equation in such a way that delta is only in the left-hand side. But we could put it in the right-hand side and be sure that the set of zeros of delta lies on the boundary of moduli spaces of genus 2, in fact, with great multiplicity.
Sorry, do you mean that all the zeros are on the boundary?
The zeros of delta, it is
All the zeros of delta are on the boundary.
it is a curve. Delta equals 0 is a curve itself. It has codimension 1. I'm not, thank you for the question, I didn't think about it. Possibly, it seems to me that yes, but I have to check. I have to check it.
And you also write that it is a free family over the genus 2 curve. Does this mean that the curve is one and the same?
No, no, no. Look, we have not yet approached the Fried family. In this family, this is the family of genus 2 curves over the affine plane, the affine FJ plane. The generic term of it has 6 critical values. And now, so here is the main hero that that was promised. Perhaps rather a nasty. It is not so clear that the curve is nice as it was declared in the title. However, perhaps I can say a few words in advertising it. First of all, this is the case when we see explicitly the piece of yes, this is what I was expecting, some laughter in the audience. Okay, so but well, let's stop for a while and remember that for some reasons we are considering not all the three-dimensional set of curves of genus 2, but only its subset, two-dimensional subset of bielliptic curves. So our F and J are just kind of parameterization of a complete piece of moduli spaces with additional automorphism. So it's two-dimensional. In it, we have a one-dimensional curve. This is an affine curve. Perhaps it's impossible to see that it has genus 2 without computers, but it has. It has. So this depends my blue explanations, exclamation.
So if it is genus 2, it means that it has many singularities.
Yes, it has, and well, it is just a funny detail that it is defined over reals, and here you see the piece of sets of its real point, and mind this cusp, please. This cusp corresponds to to one of the Belyi pairs we were looking for. In fact, this curve contains at least one rational point. May I remind you now the modal conjecture that has become a theorem, the Falting's theorem. This curve has a finite number of rational points over any field of algebraic numbers. In particular, it has a finite number of rational points, and it is difficult to find them all. I skip the nice rational curve that sits on it because I'm unable to write them down in good coordinates. But it also has the finite number of points defined over any number fields. And among the singularities, there is a pair of points that constitute the desired Belyi pair. So, skipping the details, we have arrived to what we were going to do.
Sorry.
Yes.
What about f equal to 1/2 rather than negative 1/2?
I don't think it is not marked by anything. Do you see something?
I'm just looking at the graph.
Maybe you see there much more than I do. You see another singularity here, yes? So the answer is, again, thank you for the question. I had no. We are going to study it thoroughly from several points of view, and in particular study all the singularities. So yes, Seryoja, thank you. It is really obvious that this other singularity has its f coordinate a half, as well as ours. Yes, and you see the isolated point, so it means the other sign of the square root of 2. So the
Yeah, that's what I thought, but what about
the answer is I don't know. Thank you. It's not a difficult question since I have.
Четвертая точка может оказаться как раз вот локальным максимумом.
Well, I think the good strategy is to study, well, all these finite sets of points. First, to study all the singularities, of course, carefully. It is a very easy task. And then a much more difficult task, use the modal theorem in finding points defined over various number fields. Okay, so I was going to say something about curves of genus 3, but Nikolai will do it much better. What should I do? Коль, вам освободить вот это место, да? Я останусь, да, на всякий случай. Нет, до 6 ска. Да. Ой, извините.
Okay. I guess I have like 15, 20 minutes. Half an hour. Okay. Okay. Well, probably I switched to another presentation just to. Как мне выйти? Мне свернуть, как мне вернуться на десктоп? Остановить демонстрацию. Все, я понял, да.
Потом опять демонстрацию заново.
Юра,
Почему-то она не сворачивается.
prepare. What is the automorphism group of this curve?
Of the what?
Of this curve?
We are not aware about
Any
besides
Well,
hyper-evolution.
Еще в зуме поделитесь, пожалуйста.
Так, а я только открыл это, почему-то открыл в браузере, а не в акробате. Как ее на весь экран развернуть? Это акробат?
Да, Ctrl.
А как Ctrl-L не работает? Ctrl-L не работает. Если это...
Вот там сверху плюс, нет?
Плюс, ну, хотелось на весь экран. Это браузер, это не... Ну, хорошо, давайте.
Нет, да, сейчас, в зуме нужно поделиться.
В Zoom я поделюсь, да, сейчас. К сожалению. Unfortunately, it's not a full screen. So, oh, maybe okay. Okay, I'm going to tell a little bit different approach to the topics that George talked today, probably from group theoretical point of view. And The story really started quite long ago, in like 17 years ago, when we calculated the Belyi functions, 4 Belyi functions of the smallest descents of genus 2, and here is the answer that they gave in 2005, and the main property that allowed us to make the calculations is the self-duality of these descents. Actually, when you have a descent and you have a dual descent, then you can make a union of these two graphs and get a graph with 2 more edges. And duality of self-duality means that this new descent has a non-trivial automorphism of order 2.
Not 2 more edges, but
Double. The number of edges double.
Double. Two times small. Two times small. Yes. So we get a new descent with automorphism group, non-trivial automorphism group, and we can factor by this automorphism group, and it really helps because it reduces the genus. We started with curve of genus 2 and factoring by this hidden symmetry. We call it hidden symmetry because it's not actual symmetry of the graph on the surface, but it's hidden between symmetry between graph and his dual one. And the factor by automorphism groups reduces the genus and makes the calculations simpler. And this was the way which we used to calculate these Belyi functions 17 years ago. What George told today, that we try to approach these singular points, these isolated points in moduli spaces, which correspond to this Belyi function, 4 points, from more general families of functions on curves, or from more general sets of curves in moduli spaces. What we have here? We have, as was already said, the curves are bi-elliptic, and the bi-elliptic automorphism is the automorphism which interchanges graph and his dual one, dual one counterparty. So let us consider such a family. Well, probably it's in Hurwitz space. Curve and function on this curve. So X is bi-elliptic curve of genus 2, and sigma is a bi-elliptic involution, and we are looking for rational functions with single 0 and single pole of degree 8, function of degree 8 as well. And the self-duality corresponds to this identity that functions that are looking for multiplied by, well, okay, it's written here. So in most general case, we fixed zeros and poles of this function. So we have this function branched over 0 branching with degree 8, over infinity branching with degree 8, and we have maximum 4 more branching points, and most generic branch data is have Morse branching, simple branching over 4 points. And because we require an analog of self-duality of the graph, here, the critical values come in pairs. We have critical value A, for example, A, and 1 over A, B, and 1 over B. This this family of curves is two-dimensional.
So there are two parameters.
Two parameters, yeah. So it's two-dimensional. Then we try to specify parameters in such a way that we come. Finally, we want to come to our Belyi function, which are just single points. So set of dimension 0. So first, we are going to look to the cases when the critical values collapse, merge into single one. Well, there are different ways to when critical values collapse, but let's consider when A and B collapse or A and 1 over B collapse. Then the second pair of critical values also merge into one. So in this case, we get the freed family, and this is the without formulas, but geometrically, combinatorially, this is the freed curve which George just talked about, and the equations that we are given. This is the equations for this freed curve in the moduli space. And when we specify parameters so that they collapse into these two critical values collapse into single one, then we get Belyi function. As George said, I would like to show what we can do next in genus 3. But first, I want to explain what happens here, what we like in our considerations with genus 2. And when we have a freed family of curves and functions on it with four critical values, then the
Is it a usual situation that when you consider a freed family, then a typical element of this family has two additional ramification points in addition to 0 and infinity. With ramification of type 2 to the power k.
well, we considered just a specific case.
This is a specific case.
Yeah.
For general freed family.
For general freed family, we can choose any branch data which has no symmetry in its passport. So there are.
Even if you would like to obtain a clean Belyi as a limit.
Yes, I think it imposes some restrictions. I'm not sure that the ones like you mentioned.
Well, of course, if you want to get a clean Belyi pair, then you finally need to get all ramifications are for the two. And you can split them and get freed family, but it's not the only way to get it. Of course, you can make there are much more freed families. It's George, I think he never said that this is the only freed family coming through this singular point. There are many of them, and really many, and we are considering just one because it has some nice properties. So when we have freed family, then actually it's a curve in the moduli space, and actually there is a Belyi function which is defined on this curve, on the base of Fried family on a curve, there is some Belyi function. This Belyi function can be understood as a cross ratio of 4 critical values. You have Fried family. You take a point on it, which is just a curve and function with 4 critical values, and then you take cross ratio of these 4 critical values, and you get some complex or extended complex value. It can be considered as a function on the curve in the moduli space. And this function is actually a Belyi function. It's not difficult to see. And it defines some descent, some graph on this curve in the moduli space. Usually we call this graph megamap, the term invented by Sasha Zvonkin. There is this megamap can be defined in terms of action of the braid group, a spherical braid group. I will skip it for now. Just here are formulas, and I refer to a wonderful book of Sergei Landau and Sasha Zvonkin, Graph on Surfaces in the Application. It's written there. So they got some Fried family, and the question is, what is the descent on this curve? What is the megamap on this Fried curve? From graph theoretical point of view, we can describe covers ramified over, for example, for 3 points. For example, Belyi function. We can define Belyi functions by the monodromy, by 3 permutations. The product of them is identity. They define a graph on surface, a ribbon graph or descent. And the question is how we can deform. Let's try to go back from Belyi functions to dimension 1 to Fried family. We try to split this single critical value into 2 critical values, so that we get ramifications over these 2 critical values to 2 points of order 2 over each one. It's easy to see that you have 4 involutions, and there are 3 ways to split into 2 pairs. And the braid group acts on the set of independent involutions. I mean independent involutions, right? And the braid group acts on these sets. I just to make it shorter, I didn't write here the 4th permutation. It's the same as here. It doesn't change. Just here should be 4 permutations. But actually not. So we get 3 candidates. 3 candidates how we can split into Fried family. But one of these candidates doesn't have self-duality property. So it's not what we are looking for. The other 2 have self-duality property, and actually that is what we want. Another observation is that this one which we are not looking for is rather huge. This is the graph with over 1,000 edges and of genus over 200.
That's why you call it MAGA map.
No, that's not why. Yeah, but what we are looking for is more simple. only 80 edges, just genus 8, and moreover, the mega map of these two kinds is actually it's the same mega map. They are just two different representatives of the same class. There is automorphism order 2, and factoring by this automorphism, we get a curve of genus 0. Yeah, sure, it's true. Yeah, it means that it's true. But well, actually, what we have here, we have some cover of the curve. Actually, when we talk about mega map, it's some cover of the curve in the modular space which we talked about, because there are two things. First of all, now we talk about Hurwitz space, not about modular space, so it's some cover. And another point is that to talk about mega maps, we number the critical values. We have numbered them, and actually it means that we introduce some new structure on this family, and it defines some cover of this original curve in modular space. But anyway, they are related. They are quite close and covers of order 2. And here I can draw the Zen now, because I got a curve of genus 0, and so now here it is. We call it ferro, just because it looks like a ferro. I hope you agree with me. Here's the passport of this design, and it's possible to calculate with computer, with using character tables of symmetric group to compute number of realizations of this passport. So here's the answer. It's more than 9 trillions. More than 9 trillions designs with these passports, and this one is separated from them, and as a consequence, the Belyi function is defined over rational numbers. And the side effect of the calculations which George presented us today is that we get the formula for Belyi function of this design. Well, computation of Belyi function is not an easy task, especially for 40 edges. It's quite a difficult task, but we get it just a side effect. And here's the answer to the question about Belyi function. It's written with quite small numbers. So this is the answer for this Belyi function of the mega map.
And in this case, the Belyi function itself is defined over ratio.
It's typical. Well, actually, being a mega map of with some additional properties, if some design is a mega map of some Fried family, it means that is Galois invariant. It is Galois invariant. And so it depends how many mega maps we get. Because if you start with Fried family, for example, you let us fix some branch data with 4 branch points. You get some Fried family. It's possible that this Fried family is, how it's called, reducible. You have several components. and you have a graph on each component, and but actually we describe something which is Galois invariant. So what Galois group can do, it can permute the components of the Fried family. So in this particular case, which we consider, we have single component of the Fried family, and it means that it's Galois invariant. So it's very nice. It's very interesting source of Galois invariance, source of functions defined over rational numbers. And this is just an example of many others. Well, and here's the true form. This is the pre-image of the segment connecting two critical values. Well, it doesn't look like a ferro anymore, more like an alien on a back. Well, but still, we still call it ferro. So now I would like to tell something about genus free, and so let's make some summary of what we talked today about genus 2. We talked about 4 descents, and they have here's the table. They have different automorphism groups, and it's also helpful to look for edge rotation group of or monodromy group of Belyi function or edge rotation group of the graph. Also, it's important property of cell duality, and in genus 2, all descents were self-dual. And what we talked about today, the hard case was this line. Actually, as you see here, the monodromy group is non-trivial. It doesn't mean that Fried family has this monodromy group. Then they split to, then they go from Belyi function from single point to Fried family. The monodromy group of Fried function actually is, I think, alternating group of degree 7. But these two graphs, have such a nice edge rotation group. And here is the table for genus free. Probably the next step that they're going to do. I think that here are some people that know a little bit, at least partially know some numbers in this table. Boris Bachkov with Dmitry Epifanov and Vladimir Adrianov had a paper when we calculated probably the easiest descents in this table, descents with automorphism group of 12 and automorphism group of 3, of order 3. There are a lot of other groups, other descents with imprimitive groups. Imprimitive groups means that the Belyi function becomes a composition, can be presented as a composition of other functions. So the most interesting are the 3 last lines, and you see here that there are again two descents with similar group, which probably the analogs of our descents in genus 3. And what I just talked about, mega maps and splitting descent into Fried family can be applied to these two descents in the same manner. And here we have 6 involutions, and there are 10 different ways to split 6 involution into two triples, and four four ways have a nice property of self-duality, and braid group actions have a rather small, relatively small orbits. So we have a mega map of with 312 degrees edges, and this mega map has genus 11, quite a lot. It has no automorphism group, but it's self-dual. As I already said, self-duality is a hidden symmetry, and allows us to reduce the genus by factoring. So finally we come to genus 0 graph, to design of genus 0 with 312 edges. And here is the passport of it. Unfortunately, I don't have a picture for it, but this is just something that we will get in genus 3. It is, we can see it's a clean design, so it can be written as a graph with 156 edges, non-bicolored graph, 156 edges. So that's all what I'd like to say today. So let's go back here. Here our next aim is genus 3, and probably this line looks most interesting.
Okay, thanks. More questions? Comments?
Можно спросить?
Да.
В середине докладов вы показывали некоторые семейства, зависящие от параметра t. Вот, и они, видимо, были чем-то выделены, эти семейства, что я не уловил. То есть это, видимо, плоские семейства, да? Что называется?
Вот про это.
Ну вот да, можно даже предыдущий слайд, где более простые примеры. Да, что здесь, о чем здесь?
Ну вот это как раз те конкретные семейства кривых. Кривая здесь всякий раз. Вот это семейство кривых, зависящих от параметра t. Это,
Плоская кривая.
ну, то, что она плоская, это кривая, это некоторая случайность. Существенно, что это кривая рода 2. Если у вас v квадрат есть какой-то многочлен от u, и степень этого многочлена там 6, вы получаете кривую рода 2. Если бы степень была 4, то вы бы получили кривую рода 1. А если бы степень была 8, вы бы получили кривую рода 3.
Они, значит, делают следующее. Это кривая из кривых. То есть вот каждая точка вот t это типа параметр на кривой. И каждая точка на кривой соответствует кривой. И дальше вот во все эти кривые, они выделены тем, что есть на них функция, и у этой функции 4 критических значения. Вот это вот такое типа семейство кривых с функцией. И вот есть 4 критических значения. Почему они их изучают? Потому что они хотят, чтобы на этой кривой, которая состоит из кривых, в которой каждый 4 критические значения, там лежали такие кривые, у которых 3 критические значения. Они, собственно, хотят этим искать вот эти кривые с 3 критическими значениями. Для этого они рисуют такую кривую, в которых везде 4 критических значения, и ищут такие места, где эти 4 критические значения как-то сливаются, получается 3 критические значения, и там они ищут такие красивые картинки, которые они хотели искать изначально. Вот такая цель. Я пояснила?
Вот Т пробегает что? Длинную прямую.
Ну, это сложный вопрос. Это как бы один параметр, но имейте в виду, что это такое накрытие, у них вообще получается на самом деле прямая.
В данном случае t пробегает прямую.
Да.
Вообще это такая ситуация. T типа четвертое критическое значение. Вот есть сфера, в ней нельзя заходить в 0, 1 до бесконечности. Нужно ездить буквой T. Но вопрос, когда вы объезжаете вот эти вот точки, вы попадаете в то же место или... То есть то, что мы изучаем, это накрытие сферы без 3 точек.
отсюда мы заключаем, что эта кривая определена над полем алгебраических чисел. Теорема Белого нам говорит, что на кривой есть функция с тремя критическими значениями, тогда и только тогда, когда сама эта кривая определена над полем алгебраических чисел.
Но, как я обычно сказал, что обычно получается очень невысокая степень. Невысокая степень иррациональности, например, рациональная.
Пафос в том, что мы стартуем с вот таких кривых, на которых есть функция с тремя критическими значениями, включаем их, говорим, что это у нас какие-то на самом деле точки на какой-то другой кривой, на которой вот этот параметр t есть, функция белого на самом деле. То есть опять получается вот на этой кривой, на которой они как бы...
Recording stopped.
Тоже есть функция белого, и тоже есть вот такая картинка, и тоже три критических значения. Такая вот
Это функция Фрида. Вот в этом примере, что здесь написано? Здесь написано параметризованное семейство, значит, кривых. Вот от yx, это для каждого фиксированного t, это некоторая кривая. И на ней есть вот такая функция. Вот эта функция имеет 4 критических значения.
А вот когда t равно плюс-минус 2, тогда утверждается, что что-то случилось с этими критическими значениями и стало меньше.
А можно еще тоже наивный вопрос я задам? А можете нарисовать картинку, когда у графа, объединенного с его двойственным, имеется инволюция?
Ну, автоморфизм.
Автоморфизм, картинка.
Всегда. Любой граф. Давайте любой граф нарисуем. Давайте нарисуем.
Да.
Функция белого применяется. Остается функция белого.
Вопрос в чем-то другом.
Нет, там же было где-то, вот в вашей части, что берется граф, его двойственный, вот это понятие самодвойственного.
Так, ну, давайте я сейчас
Ну, не знаю,
немножко научу.
возьмите трактор.
Да. Так. Давайте самый простой. Давайте возьмем двойственный граф. Значит, у него вот никаких автоморфизмов нет. Давайте возьмем двойственный. Что такое двойственный? Есть две центрограни, мы проводим вот так вот и через серединки ребер. И вот так. Получился вот такой вот рисунок. У него есть автоморфизм, утверждаю я. Значит, автоморфизм. Ну, давайте я нарисую, значит, еще раз. Вот. Один круг, один цикл, второй цикл. Значит, вершинка здесь, вершинка здесь, вершинка здесь.
Вот понятно, вот это был мой вопрос. Что значит объединение графа и двойственного? Они объединяются не связанным образом, а прямо на той плоскости, где они...
На той поверхности.
На той поверхности, да.
Где они
На той поверхности,
понятно,
да.
понятно.
Ну, потому что вот значит, это было бета у исходного рисунка функции первого. У двойственного будет 1 поделить на бета. Значит, функция, которая функция Жуковского, функция бета, она тоже функция белого, как раз вот этого рисунка. И у нее есть автоморфизм, который переставляет моли бесконечно.
Okay, I have more questions, but I'm afraid we should stop here because the next seminar starts in a minute or so.
У нас есть докладчик?
Спасибо большое.
Боря, а вы... Что там нужно сделать?